This lesson is part 3 of thermochemistry, and we're going to be talking about how to solve for the delta H of a reaction in a different way. So we've already talked about 2 ways, and this is just a different way called using heats of formation or enthalpies of formation. And it's on page 9 and 10 in your notes. So reminder, enthalpy is the gain or loss of heat during a chemical reaction. And there's, again, a lot of different ways that we can get those numbers. So one way is using a table of data that's already been collected, and these data numbers are called enthalpies of formation. So it's delta H, and it has this little F subscript on it, and that stands for formation. The definition of what these numbers are is listed right here. So it's the enthalpy change associated with producing 1 mole of a compound from its elements in their most standard states. So if you start with just elements from the periodic table and you make these compounds like ammonia or nitrogen dioxide or water, if you make those from their elements, these are the enthalpy changes associated with that. So if we take a simple one right here like H2O, and we wanted to write that chemical equation, we would form H2O from its elements, which are H2 and O2. And by definition, this has to form just 1 mole of the compound. So to balance it, we're actually going to use a fraction, which is a little bit unusual, but it allows us to maintain that coefficient of a 1 right there. So this is forming 1 mole of water from its elements, so its delta H is the value from the table. It's negative 286 kilojoules. So that's the definition of what these are. You'll notice that elements are not listed in this table. You have to just know that elements are 0, because if you think about it, forming an element from its elements is going to be 0, because if we want to know the value for oxygen, well, you're going to form it from oxygen, and the delta H of that would be 0 because nothing's happening. So you simply have to know that the values for elements are 0 and they're not going to be listed. So Hess's law can be summarized into this equation that we're going to be using today, and this is just called the summation equation. Basically, you take those values, those delta H of formations, and you take the values for all the products. That little symbol right there means the summation or total. So you take the value for all the products and you subtract the values for all the reactants. So I frequently just say products minus reactants. The thing you have to remember is that you have to multiply those delta H of formations by their coefficients. So we're going to look at a lot of examples today. So main idea, the delta H of a reaction is the total delta H of all the products. You multiply the values by their coefficients from the balanced equation, and you subtract the value for all the reactants. So another way to write out this equation, if you have 2 reactants and 2 products, the summation equation would look like this. So you have the delta H of formation of the product and the other product, and you subtract this reactant and this reactant. So it's product plus product minus reactant, and all of them are multiplied by lowercase n, which simply stands for the number of moles of that chemical, or the coefficient from the balanced equation. So we're going to do a couple of examples here. So we have this chemical equation here with CH2N2 reacting with oxygen to form 3 products: carbon monoxide, liquid water, and nitrogen. So first we look at what we're given. We have the table of data given to us right here. And notice that it's only 3 out of the 5 chemicals. Nitrogen and oxygen don't have values, again, because they're 0 because they're elements. So let's work this out. So this one's going to be 1, 2, 3 products and 2 reactants. So our basic setup for this one, the delta H of the reaction, is 3 products added together minus 2 reactants. So that's our basic setup. So here we go. So down here we'll show our work. Delta H of reaction is, our first product is carbon monoxide. So we just take 1 of those. So the carbon monoxide value is negative 110.0. We add, and I'll put a little check mark by that one. Next we move on to the H2O liquid. So we add 1 of those, negative 285.9, and we add, put a little check mark there. Next we add our nitrogen. Well, that one's 0, so I'm not even going to include it. Now we subtract our reactant. So I'm going to change that to a minus sign. We subtract our reactant. So CH2N2, we're going to subtract that value, the 62.4, and then we're going to So check mark there. And then we're going to subtract the oxygen. Well, that's subtracting 0, so I'm not even going to show my work. So this is our setup. So we're going to get our calculators out and do this calculation. So negative, let's turn it on, negative 110 0.0 plus negative 285.9 minus 62.4. We get negative 485.3. For sig figs on this, all of our values that were given went to the 10th place, so our answer can go to the 10th place. So negative 485.3 is our answer. And that is kilojoules for the moles of that particular reaction. So that's pretty much it. Again, main idea, you take your products minus reactants. Now this example, what it didn't have was any coefficients. So our next example is going to include that as well. So example 2, we're going to calculate delta H for this big long reaction here. And again, we see that we're going to have some coefficients involved. So here we go. Delta H of the reaction is, again, we have 4 products, so I'm just going to write this out. You don't have to show this as part of your work, but it's going to be 4 products added together minus 2 reactants. So that's our basic setup. So our first product is aluminum oxide, which is right here. So negative 1676. I'm going to add my next product, aluminum chloride, one of those. So negative 704. Next, I have 3 nitrogen monoxides. So this one's going to look a little different. We have to remember to multiply by 3. So 3 times the value of nitrogen monoxide, which is 90. So there we go. And then 6 waters. So plus 6 times the value of water, which is negative 242. I'm going to continue on down here. Now I'm going to subtract my reactants. Well, aluminum is my first reactant. That's an element, so it's 0, so you don't need to show it in your work. I'm going to subtract 3 ammonium perchlorates. So minus 3 times the value of ammonium perchlorate, negative 295. So that's your setup. We did products minus reactants, and we multiplied each one by its coefficient. Let's switch to our calculator and solve. So we take negative 1676 plus negative 704 plus, we're going to use some parentheses here, 3 times 90 plus 6 times negative 242 and those are all my products added together, and then we subtract our reactant, and we had 3 times negative 295 for that. Now on this one, it looks like I can only answer to the ones place for sig figs, and luckily it kind of works out that way. So negative 2,677 is my answer. Negative 2,677 kilojoules. So that's another good example of just showing how to solve for the delta H of a reaction. Products minus reactants, you multiply by all the coefficients. Was this reaction exo or endothermic? This is something to keep in mind as we go through this. This one was exothermic, and we know that because it had a negative delta H. All right, 2 more quick examples. This one's going to be a little bit different. We're actually going to solve for the delta H of a compound rather than the delta H of the reaction. So the delta H of this reaction is already known. They're telling us that 2,800 kilojoules is a product, And if heat is a product, we know that it's exothermic. So we know that the delta H of this reaction is negative 2,800 kilojoules. Again, we know that it's negative because it was exothermic. So we're going to keep that in mind as we solve for the delta H of this chemical right there. So delta H of this reaction, again, is negative 2,800. We're going to still do products minus reactants and multiply by coefficient. So first we have 6 times my first product, CO2, which has the value of negative 393.5, plus 6 waters, so 6 times the water value, which is negative 285.9, minus my reactants. Now, this one, here, that one got a check mark. This one is my question mark. We don't know what that one is, so we're just going to call it X. And oxygen is an element, it's 0, so just forget about it. So here's our setup here, and we're just going to do some like simple algebra and solve for X. So let's get to work on that. So we start with negative 2,800, and then we're going to move these other ones over to get X by itself. So we're going to subtract 6 times carbon dioxide's value, negative 393.5, and then we're going to subtract 6 times water's value, negative 285.9, and that would move these over, but that is negative X. So our final step is to obviously change the sign, so times -1. Hopefully you don't really need to do that in your calculator. So negative 1276.4. And this one, I guess technically we should only go to the hundredths place on this. Let's pretend there's a decimal there and go to the ones place. So negative 1276 is going to be our answer. So negative 1276 would be the value in the table for C6H12O6. So that's our answer. That's the delta H of formation for that particular chemical. All right, one more example. This one is only different because you have to use the entire table and you have to sort through and find the ones that you want. So we're going to use those enthalpies of formation to find the standard change in enthalpy for this reaction, which is called the thermite reaction. You may have seen this on YouTube. If you haven't ever looked for the thermite reaction on YouTube, you should. It's a pretty spectacular explosion. So we're going to solve for the delta H by doing products minus reactants. So here we go. Last example. We have aluminum oxide as our product, just one of them. So aluminum oxide is negative 1676 with 2 irons. That's a pure element. It's a 0, so ignore it. Minus reactants. Well, our first reactant is aluminum, pure element. Ignore it. And then we have iron oxide. So iron oxide is here as negative 826. So minus negative 826. So simple calculation. Let's grab our calculator and finish this out. So negative 1676 minus negative 826 so negative 850 kilojoules is our answer. So again, that's a very exothermic reaction. It's a big negative number. If you look it up on YouTube, you'll see that it's a very, very exothermic reaction. It releases a lot of energy, and it's pretty spectacular to watch. So that's our final example. I hope this was helpful. Thanks for watching.